Hello, welcome back. Today I'm going to continue friction. If you recall last time, after having discussed the three fundamental forces, namely tension, the manifestations of electromagnetic force, tension, normal force, spring force, and then I'm doing friction. Although this is given as a separate chapter, I'm going to combine it with the Newton's laws of motion only and giving you all the possible minute details of friction. I tried to remove some of the misnomers regarding friction in my previous lecture. This is lecture number Dynamics 13. In this, of course, I'm going to continue with the limiting friction. Actually, we were looking at what is the force exerted by one body on the other. That means contact force. The contact force need not necessarily be only normal force, only frictional force. In fact, it's a combination of both. Well, if N is not there, F doesn't arise. If N is not there, F doesn't arise. Just because N is present, F need not be present. This friction is a variable till the body starts moving, or is about to move. That is what we call the static friction. So in which case, we take contact force as this. If it is a limiting that's about to start, then this is the scenario. So we have shown you here how do you get this. I'm going to continue discussion on this. How I do that you can see now. You see, this is the resultant contact force. When the body is just about, the moment I write L, that means body begins to move, is about to move, not yet started moving. And in such a case, angle between Fc and N is called angle of friction. Angle of friction. Now, this is a right angle triangle. I can write tan theta F as opposite. What is opposite side? Well, this is Fc, this is FL. FL by, N. But what is FL? Or what is theta F? Tan inverse mu L. That means I can write it as sine inverse. This is opposite side by 1, that is your adjacent side. Therefore, you get mu L upon root of 1 plus mu L whole square. You can also write this in terms of cosine inverse 1 upon root of 1 plus mu L square. In any form you want, you can write. You can write it as cot inverse 1 by mu L, secant inverse root of 1 plus mu L square, cosecant inverse root of 1 plus mu L square. I just purposely wrote this. The moment you know one, all others are automatic. So do not look for options only in terms of tan inverse. In fact, trigonometry could be, misleading sometimes if you try to memorize these things and then confine to only that. Likewise, you can do it. Okay? Now, you have introduced this theta F here. We have introduced mu L, theta F are absolutely related. Whatever the factors on which mu L depends, your theta f also depends. So what factors these two would depend? One, nature of surfaces. That means are they more rough, less rough, etc. Nature of material. You see, when I talk of mu L or theta f, I will never talk of a single body or single substance, because unless two bodies interact, you will never get a mu L or theta f. Therefore, whenever we say nature of surfaces, nature of the material, for example, I have a concrete road and there is a tire that is made of rubber. So rubber and concrete, iron and concrete, copper and copper, copper and rubber, rubber and you can have any. In fact, all these things are experimentally determined. Nobody would derive them theoretically. Based on the experiments, they will get these values and they are tabulated. So particularly in engineering applications, you will be knowing what these values are and accordingly you can use them. Okay? So that is the nature of the material and the nature of the surfaces. Relatively smooth, less. Relatively more rough, the value is more. Likewise, you will have it. Both theta f and mu. But never depends on normal force or effort. It's a very beautiful concept that we in general come across in scientific applications. What do you mean by that? You said Fl is proportional to N. Fl is equal to some constant into N. This constant may depend on several parameters, any parameters except these two from which you have derived. I'm going to make this a universal statement. The constants of proportionalities never ever depend on the parameters from which it is derived or they are derived. For example, F is proportional to M1, M2, inversely proportional to R square. The most famous law of gravitation is called universal law of gravitation. And when you do it, you remove that proportional, you will introduce a constant which is incidentally known as universal gravitational constant. So far so good, it has its own units. These may have units, may not have it. For example, this doesn't have any unit, but this has units. It's possible. But I'm talking of the dependency. Now, if I write this, G Fr square by M1, M2. Supposing you are given such a relation, what will be your idea to start with? If M is more, G is less. Do you agree or not? Based on this formulation, what I will think, it is inversely proportional to the masses, directly proportional to the square of the distance, directly proportional to the force. So where is that constancy? Where is that universal constancy? Do you understand? That is why physics is very ticklish in certain aspects. In mathematics, this is correct and this is correct. In physics, this alone is correct, this is wrong. Although in maths, you are free to take any parameter onto the other side, this onto this side, etc. But in physics, you have to be very careful. Why? Because it's going to tell me that G is dependent on all these factors. The fact is, G never depends on anything, in fact, in this unit, but definitely not on M1, M2 or F. If M changes, F will change. If R changes, F will change to make G constant. Luckily, there you have got that universal gravitational constant. Therefore, you are able to talk in that sense. But then, if you look at in reality, that is not the case. So, we will never ever write in this fashion. Although, dimensionally, mathematically, technically, this is not wrong. But in physics, it is not accepted. So, never ever depends on n. Suppose normal force is doubled. There is a body here. On this, I am pressing it further and further. So if I want to move it, then probably the minimum force required to move that may change. But mu will not depend on n. But this is a very, very important point. So remember, FL and N are related, but not mu and F nor mu and N. Mu is a typical characteristic feature of the given substances. You will talk of only pair of surfaces. Now, well, this is the angle of friction you have learned, and there is no limit to this theta or mu. Mu can take any value theoretically. What do you mean by that? Mu can vary from 0 to infinity. Strictly speaking, this is ridiculous. This is equally ridiculous. But in this case, I may probably call it as perfectly smooth. Generally, you have values between 0.3, 0.4 or 1, possible 1.1, 2, 3. See, there is no limit for this value. Mostly we come across in the range of less than 1, sometimes more than 1. Likewise, it is possible, but otherwise, you will never come across values that are that close to infinity, likewise, okay? That is the limits of mu. I told you on what factors this is different, but now one very important thing. For example, here is a body, okay? There is another body, okay? Two bodies, 1 and 2. So this is a rough surface. Now, as I said, friction is necessary, but you can't bear it if it is too much. So, we call friction a necessary evil. Beautiful words, isn't it? Necessary, but evil. Required, you can't take more. Salt. Salt is required in any of the foodstuff that you generally prepare for eating. But if you put more salt, you'll throw it off. So you can't. Some people take more salt, some people take less salt, that is fine. In a similar way, everywhere friction is a must. But in excess we can't bear because it causes wear and tear. It causes wear and tear. When a tire, the wheels move on the concrete roads or the tar roads that you have, you have a grater in your house. You take some, say, carrot or beetroot or something, and then, so likewise. You keep on grating it. You can see the grating. You can see how that whole of beetroot is coming down and ultimately there is nothing left on that. This is what's going to happen on the road in real situations, but not visible. If you are able to do a beetroot in a span of around a couple of minutes, maybe for the tire to get wear and tear to be visible, you may take a couple of years or 3 years or more, depending on the quality of the tire and the types of roads on which you would in general travel with them. I hope you are able to understand that. So, this is what it does. The friction does like this whenever it is in excess. So, what is the tendency for you to reduce friction? Generally, we say apply oil and grease. Why? All these undulations. Now, I told you that if you have a microscope and view that entire surface, it's no longer smooth. Now all these are filled with some extraneous substance. So that when I put this body on this, there is a tendency for it to slip or move rather easily. That is the purpose of this. Second, maybe try to smoothen it out. Now, this is a very important concept. A rough surface is there, try to smoothen it out. You take some rough paper and then start applying. At one stage, it gets smooth. By chance, supposing if smoothness goes beyond a limit and gets quite close to perfectly smooth surface, although it's not possible in nature, but still, if we go close to the perfectly smooth surface, what's going to happen? Both surfaces are perfectly smooth. Say, for example, an iron cylinder, cut it into two parts, and then both surfaces are made to be absolutely smooth. And the moment you bring them close, automatically it gets stuck to each other. Tremendous force of attraction exists between them. Why? Almost all parts of the body are in contact. Therefore, the so-called molecular attractive force is extremely predominant. So much so, sometimes it is impossible for you to slide these two types of smooth surfaces on one over the other because of unusually strong molecular attractive or adhesive bonds. When it was rough, what was happening? Not all parts were in contact. There was a trapping, interlocking, fine, there's no interlocking. But then almost all parts are in touch. All that is on the surface, they are bound to have a very, very strong bond there. So it becomes very difficult for you to slide one over the other. For example, when you take these things into a vacuum chamber, everything is flushed out, including the air. And in such a case, you bring them and try to slide one over the other, it is impossible to do it. In fact, when you want to attach two bodies, what do? Practically you go to some welder and he will heat it and then bring them together. And the moment they are brought together, he again cools it off. So that at the time when it was very hot, they get stuck to each other. And this is how welding is done. Or you put some material and all that. But here, without heating, without putting anything, I am able to achieve what I am supposed to achieve by taking to a welder. Without heating, I welded it. That's why it's called cold welding. It's called cold welding. In fact, some of the vacuum brakes apply on this principle for your information. So, just because somebody says smoothness is required to reduce the friction. If you go beyond a point of smoothness, friction will increase. That's a very important point. I told you why it increases, because all points are virtually brought into contact with the other surface. Therefore, the forces are extremely strong intermolecular. So very difficult to break those bonds. That is why. Now, why I said it the vacuum chamber, because if I bring it outside, however much you say that nothing can penetrate, air does indeed has that ability to penetrate. And the moment it gets in oxidation that leads to corrosion. So there is an extraneous substance, therefore the whole thing gets loosened and you can immediately separate these two or slide one over the other. That is the story of it. So although smoothness is required, one cannot do beyond a point because it leads to a process called cold welding, right? Therefore, be careful that whenever somebody says something, you cannot. It's like work very hard, read a lot, throughout the night you sit and then read. Next day morning when you go to the examination hall, you will sleep there. Or you come to the classroom, you will not listen to anyone. So this is not the way. Never do anything in excess. Ati sarvatra varjayet. Ati sarvatra varjayet. This is one very important. At the same time, makes no mistakes he who makes nothing. Somebody saying he doesn't commit any mistakes. Why? Because he doesn't do anything. So that is another extreme. When you do ati, this is another extreme. So I would expect you to do neither. Be careful that you have to be always balancing and in between the two. Then only you can reduce the friction there. Is that clear to you? Right. Now, if you see, I will tell you, there is a FL, that static limiting friction, then there is a kinetic friction. So generally associated with this mu L, associated with that is mu K. Now, for a given pair of surfaces, I am talking of, say, copper over copper. Mu L is more or mu K is more. Then immediately I will say mu L is more than mu K. But this is for a given pair of surfaces. Unless you make such a statement, this is not going to be valid. Which pair you are talking about, you specify. You can't take mu K from one pair and mu L from some other pair, and that's why for a given pair only this is valid. Why you can say due to inertia. Why mu L is greater than mu K? Due to inertia. Now I tell you, say for example, mu K, now you have the same two surfaces. What I would advise you, don't do it. Any experiment I say, please do not attempt it. Just follow it. It's all theoretical experiments or thought experiments. What I would say, take two bodies and you want to bring them together by applying some adhesive. Say, take some normally available adhesive, you apply and put it, and if you remove it, it will come off immediately. But if you wait for some time, the bonds are established, then it becomes a little more difficult. Wait for some more time, it becomes extremely difficult if the adhesive is very perfect to slide one over the other. You understand? In a similar way, when one body is on the lying on another body, another surface, to just move the body, I may be applying a huge force. Why? Because there is sufficient time for the molecules of both the substances to establish the bonds, molecular bonds. The same surface, if it is on the move, every time it moves, it is coming into contact with a new set of molecules, and before the bonds are established, you are moving off. So you are not allowing sufficient time for the molecules to establish adhesive bonds. I hope you are able to understand. Therefore, whenever body is in motion for the same pair, mu k is in general less. Don't think that if mu k is 0.1, mu a will be 3 or 4. No. The differences are, of course, extremely small. Maybe if it is 0.9, this may be 1. Or this may be 0.6, this may be 0.65, something of that sort. All depends. All depends. Okay? So that is very, very easily for a given pair of surfaces, I will say mu is greater than mu k. Same thing if somebody asks you, FL is greater than FK. I know the tendency of many a people, many a person is, it is true. That is how people talk. But I would say, not necessary. Why? Now, here is one body. Suppose I take for a given pair so that mu L, mu K are fixed, and for a given normal force. Now this is crucial. I am telling you why it comes into play. Suppose I take a toy car with wheels made of rubber, very small toy car, something like this. Okay? Mu L may be 0.9, mu K may be 0.8. Now, the same concrete surface, I take a huge lorry or a truck. A huge truck. This material is same. The same surface, same mu L, mu K. For you to start moving this truck, you may be probably requiring few thousands of newtons. Whereas to just move it, you may require hardly 1 newton. The minimum required force to just move the body, you may equate it to limiting friction. I'll describe that in a little while from now. Therefore, same pair of surfaces, but here Fk, what is Fk here? Maybe 999 newtons. What is Fl here? Fk is more than, far more than Fk, although for a given pair of surfaces. That is why, whenever you compare Fl and Fk, normal force must be fixed. For a given normal force, for a given pair of surfaces, yes, Fl is greater than Fk. Is that clear to you? Right. Then, we will take a case. Trying to produce that motion in this body, and I want to plot it. This is frictional force, this is applied force. Now I am taking, let me presume that if 20 newtons is Fl for this. So what do you mean for 10, 15, likewise? Whatever you apply, same thing would manifest there. So finally, what are you getting? Till you go to 20, now be careful, I will say applied force, 0, 0, 10, 10, 15, 15, be careful, 18, 18, here Fk is 18. Body at rest and you are trying to apply 18 newtons. This body will not move. Why? In order to just move the body, you have to apply a minimum force of 20 newtons. What is the significance of Fl? That is the minimum required magnitude of force to just displace the body. Minimum required magnitude of the force just to displace the body. Therefore, although Fk is 18 for this pair, when I apply from state of rest 18, it's going to be 19, 19. Supposing I go to 20. Immediately 20, but it starts moving, so falls to 18. What do you mean by that? Likewise, it falls to 18. And no matter what force you apply, that frictional force remains constant. So, this is Fs. This is Fk. And this is Fl. For a simple case, I'm trying to show you will get a kink. You will get a kink here and then go. Okay? 0 to 20, at the instant you apply 20, immediately it becomes 18. And if you continue to apply 20, body would accelerate. Why? Applied force is 20, opposing force is 18. So 20 minus 18 is equal to mass into acceleration. Now, for example, I continue this diagram here. 25, it still is 18. I am coming back to 20, 18. If I come back to 19, also it is 18 only. I come to 18, it is 18. And here the body moves with uniform velocity. Now, 19 newtons, if somebody says I am applying a force. Frictional force can be 19 if the body is not moving, or frictional force can be 18 if the body is in motion. Whenever the value applied force lies in between Fk and Fl, the answer could be F direct or Fk. If it is moving, Fk is the answer. If it is not moving, applied force, whatever you apply here, that is the answer. For that purpose, I have given you all these details. Okay? Okay. Right. I hope this is clear to you now. Fine. How do you interpret Fl? One is maximum static frictional force, minimum magnitude of F to just move the body. Now, suppose I am saying Fs. This is N, this is EMG, this is M. The fact that I am keeping Fs here, it indicates that the body is not moving. What is contact force? Fs square plus N. In this case, N is equal to mg So, what do you write for Fs? F square. This is the contact force. Never try to use mu here. When frictional force is static, mu doesn't come into play. Is it okay? That one. Very, very important point. Area of contact. Does the frictional force depend on the area of contact? A very standard question that people ask. Now, I take a table with only 4 legs. The contact is only at those 4 legs. But if I take the same table by covering the ground-based contact with complete wood made up of the same substance, and I want to move it, you know, both require the same amount of effort to move it. Because that so-called frictional force is independent of area of contact. This is a very important point. Why a small area may have more contact points? Small area, but now many contact points. Large area may have a very few, far less number of contact points. To move this, you don't expect much friction to develop there. But here maximum friction develops. So for definiteness, you can never say more area, more is the friction. Less area, less is the friction is not correct. Yes, more number of contact points, more is the friction. Less number of contact points, less is the friction, but you can never convert that with area. Ironically, rolling friction depends on area of contact. More the area, more is the rolling friction. Of course, although I said in the beginning, I'm not going to discuss rolling friction at all because you don't have it in your syllabus. I hope this point is clear to you. Okay? Now, once I apply, so how, if the body is about to move, then I will write FL there, M here, MG there, FL, MG. How do you write it? You know, under root of what? FC. This is already, I have kept it before so that you can use mu also, you can do that. There is no problem, whichever way you wish you can do. And you want to substitute MG, accept it, no problem. Okay? This is when you apply FL. Supposing I am increasing this force. This is your N and G. Then this is bound to be Fk. What is the acceleration? F minus Fk is ma, N is equal to mg. Likewise, you are going to get. I hope this is clear to you. When does it accelerate? We see. If you bring that force down to a value below Fk, the body would come to a halt. It rests. That's how it is. Is this clear to you? Yeah. Now, with this fundamental points, I'm going to look at in great detail. First, we will look at the static frictional force. One by one. Then minimum required force to just move the body one by one. by one by one. And then go to two body systems in friction. Okay? So we'll give a break here and then continue in our next class.